So we already went through all of our trig stuff. Here's the main idea. That trig stuff that we went through, what kind of triangles does that help you figure out? Right triangles. So this is like the big idea so you don't use the wrong things in our units. Oh, hey, how you doing? All right. Cute. Kicked me out. Okay, so right triangles, okay, are the triangles that you have been solving kind of forever. Those are the ones you know the most about. So right triangles, we can use Pythagorean theorem and we can use trig. You cannot use those things on any other types of triangles. Those only work for right triangles, okay? For every triangle, we know the angles add up to 180. So what mathematicians did is when there was a non-right triangle, you don't have to write this part down. I'm just going to give you some idea. Like, so let's say I had a triangle. It wasn't a right triangle. And I knew some angles, like maybe I know that this one's like 35 degrees or something. And this side is like 18. And I'm supposed to find the other stuff in the triangle. Okay, at first that seems somewhat impossible. So what they would do is they would like, well, I know a lot about right triangles. I'm going to draw an extra piece and split it into a right triangle. And then now they'd be able to use like sine and say like sine of 35 equals x over 18. Then with the x, they could use Pythagorean theorem and find this other part over here. And then they would just keep working on two triangles to find all the different pieces. So eventually, when mathematicians have to do lots of work, they try to summarize it in a formula so that we don't have to go back and emulate all that work that they had to do. Okay, and so they came up with two formulas that can help us in two different ways for triangles that are not right triangles. So try to understand the strength of what you're learning today is that you have something now that you could use in a triangle that's not a right triangle. So any triangle that's put in front of you can use the things we're talking about today. Okay, so the first formula that they came up with, we're not going to derive it, we're just going to look at the formula and make sure we know how to use it, is called the Law of Sines because they used the sine function like I just showed you to kind of develop what you could do every time. And it basically said, it turns out that in any triangle, the sine of an angle divided by the side across from it is equal for all of the angles in the side across from them. So if that means like if I take the sine of angle A and divide it by side A, I get the same answer as if I take the sine of angle B and divide that by side B, and I get the same answer if I take the sine of angle C and divide that by side C. Now this is the way they write the formula. Don't be confused. I'm not now introducing this whole like, guess what? We're going to solve things with two equal signs. No. Okay, the meaning of the formula is you don't have to specifically use A and B. You can use any two of these and set them equal to each other. Is that okay with everybody? So they just found out like, hey, there's this cool relationship in any triangle. If you take the sine of an angle and divide it by the side across from it, you get the same answer no matter which angle and side combination you use inside the triangles. Okay, so this is what the formula looks like. We're not going to use it setting three things equal to each other. We're always going to use two. Right? And so then we're just going to look at how we would use that in triangles and any specific questions you guys have on like getting through the solving of the equation, because sometimes when they look a little different, we get a little bit confused. Okay? So here's a triangle. Okay? It says use law of sines to solve. I'm not going to tell you. So the point is that you're going to get to a place in this class where you're like, I have all these tools, Pythagorean theorem, right triangle trig, law of sines, and then we're going to see the law of cosines, and you're going to determine which one is useful. When we look at this triangle, we're supposed to solve the whole thing. So remember what we talked about for those of us that struggle with what solving the whole thing means, that there's 6 pieces we're really interested in, 3 sides and 3 angles. And the labeling I'm talking about is using like the side across from an angle as the lowercase. So like the 20 in this case would be lowercase a, lowercase c, lowercase b. So yeah, Ainsley. Uh-huh. Yeah, you totally can. Yeah. I just like the little letters because then I don't have to write 2 of them. But you totally can label it however you're most comfortable labeling. Okay? So we already have that side A is 20. We have that angle A is 40 and angle B is 60. What could we quickly figure out here without knowing anything new? Yeah, angle C, right? All triangles are supposed to add up to 180 degrees. That's not a right triangle rule. That's an every triangle rule. So far, this triangle has 100 degrees, and that would leave 80 degrees for angle C. So we figured that out. Do you see now why you can't use Pythagorean theorem, though, or any of your sine, cosine, tangent ratios, right? Because you would have to identify the hypotenuse of this triangle specifically across from the right angle. And where is the right angle? It doesn't exist, okay? So those tools can no longer be used, and that's why we have a need for something like this law of sines, because we don't want to have to build our own right triangles within this, okay? So once we get to the point where we know we can't use right triangle stuff, you're going to have two tools. Right now you only have one, law of sines and law of cosines, and you're going to decide which one is easiest to use. The law of sines formula is a little simpler than the other, so I kind of always want to use that one first if I can. But remember how it was built. The law of sines was take an angle, sine of an angle, and divide by the side across from it. That means you need to have like numbers for those things across from each other in order to use it well. In this case, that works well because we have this 40-degree angle, and across from it, we have the side of 20. So we know what everything's supposed to work out to be. Sine of 40 divided by 20 works out to be some number in this problem, and we're supposed to get that same thing every time we do another operation like that in this triangle, okay? So we're going to either try to find side B or side C. It doesn't technically matter in this case, all right? Which one do you guys want to find first? C? So if I'm trying to find C, then I want C to be the variable in my equation, and it's a side length, so it's doing the dividing. And that means I better have the angle across from it. Do we have the angle across from side C? This angle across from it is 80. So this, okay? And then how would we solve an equation that matches this setup here? What can we do? We can just cross multiply, okay? If you guys like that better to get rid of all the fractions. Okay, some of you that have different algebra skills can rely on those as well, but cross multiplication tends to be something you guys are pretty comfortable with. So 20 multiplies the sine of 80, and C multiplies the sine of 40. And then remember, my goal is to solve for C, which means to get C alone. And what's the final step that has to be taken to do that? Good, divide by sine of 40. So C is going to equal whatever I get when I do this calculation. So when we do 20 sine 80 and divide it by sine of 40, we get 30.6. Is everybody okay with how I approached this setup? You won't have to memorize these formulas. They'll be up all the time. So your goal here is really to process how to use them correctly, like know what the parts of them represent and how we would set them up. So is everybody okay with how I set this up? Okay. That's your first kind of self-checking. Like, am I okay where all these things came from? And then do I understand how we solved the problem? Any questions that immediately come to mind for those? Okay, so then the last thing we have to find is side B, and here's where a lot of people make a mistake because you get really excited when you have two sides of a triangle, and then a lot of you want to go use Pythagorean theorem to find the third side, but we can't do that here because it's not a right triangle, all right? So in this instance, we have to use trigonometry again, not your basic trig ratios, but this law of sines idea to figure that out. And we can use almost the same equation. We can still use sine of 40 divided by 20. But this time we want to solve for B, okay? So we're going to do sine of 60 divided by B. And so again, we cross multiply. So B multiplies with the sine of 40, and 20 multiplies with the sine of 60. And to get B alone, we're dividing by the sine of 40. And when we do that, we get 26.9. And then if you're concerned about errors, our little quick check to make sure we didn't screw anything like really, really bad up works. Larger angles should still be across from larger sides, and smaller angles should still be across from smaller sides. So like my largest angle in this triangle is angle C at 80 degrees. Is the side across from it, side C, the biggest side of the triangle? Yes. Okay, and then my smallest angle is 40 degrees. Across from that is 20. That's the smallest side. So it at least seems to make general sense that this could work. All right. Any questions about setup or solving using the law of sines? Okay, we're going to do one more this time where like more of the angles are missing rather than the sides, so you can just see solving it a little bit differently. Okay, so there's one more example on there. Okay, so reasons why this triangle we would want to use law of sines. So first of all, you can't use Pythagorean theorem or your SOHCAHTOA ratios because there's no guarantee this is a right triangle. I mean, maybe it is, but I just don't have enough information to guarantee that. Okay, so you can't use those things. The next reason why this law works well, remember, it's about a relationship between an angle and a side across from it, and we have one of those. We have this angle and this side across from it. That's going to build one of our ratios and give us a little bit of freedom in the other one to have a variable. So I'm going to go ahead, label again. We're looking for the three sides and the three angles if we're solving. And we know little b is 57 and little a is 63. We know that angle A is 42 degrees, and we have no other information. So in this case, we don't have a lot of options. What is the only thing I can actually solve for right now? Angle B, okay? Can't use Pythagorean theorem because it's not a right triangle, so you definitely can't find your other side length. You have this angle and this side across from it. The only other piece of information you have is this side, and it would correspond with angle B. So that's like the only other ratio you can build where only one thing would be missing. So our ratio would say sine of 42 is across from 63. So we'll set up that ratio. And we can set that equal to the sine of angle B, and that's across from 57. Okay. So if you want to take the same approach, it's technically one extra step to cross multiply, but a lot of you guys like having a consistent idea to do this, so I'm just going to do it that way anyways. If you cross multiply, 57 multiplies the sine of 42, and 63 multiplies the sine of B. And what would I have to do at that point? I have to divide by the 63. Are you guys okay with that idea? Because we're trying to get B alone eventually. So I'm going to divide by 63 to try and cancel this out. So I have 57 sine 42, all divided by 63, equals the sine of B. How am I going to get B alone? Yeah, I'm going to have to use the inverse. Are you guys okay with that? If you're really uncomfortable with that, then go ahead and turn the fraction on the left side into a decimal. Okay, so if I do 57 sine 42 and I divide that by 63, I get a very long decimal. You're totally okay with doing this, but just do me this favor. Don't round the decimal. Keep like 4 or 5 digits of it because you're not done with the problem. And if you round it at this point to something with only like 1 digit in it, then you guys are going to get very different answers than what's going on. So if you don't like putting all that in together and you want to make a decimal, go for it, but keep at least, I'm going to keep at least 4 digits of this decimal. Okay, so again, I took this step for those of you that really don't like looking at all that algebraic stuff and trying to understand the inverse sign of that. When you look at it like this, it might make a little more sense, okay? This was actually like in our beginning notes. What do we do when we have something that says sine of an angle equals something? Then we take the inverse sine of each side. So we really have the inverse sine of this decimal will be equal to angle B. And then that's what I'll put into my calculator with all 4 of those digits just to try and not lose some of the accuracy. And so then I get 37.25. So we'll call it 37.3 degrees. Okay. Is everybody okay with the setup and then the solving? So ask yourself, like, do I understand how she set it up? Do I understand the steps to solving? And then if a question pops up, let me know. So any questions on what you see up there to get to that point? Okay, what would you guys do at this point if your goal is to figure out the rest of the information for this triangle? We're missing one angle and one side. What's that? Good. Add the angles up and subtract from 180. So we'd want to add 42 and 37.3. And then we'd want to subtract that from 180. And we would get 100.7. Okay? And so that will be angle C. Now, how will I find side length C? Somebody besides McKenna, she's given us a bunch of the answers, or Paige, because she's told us to. How are we going to find side length C? Here? Good. Okay. We're going to use the law of sines. We can't use Pythagorean theorem. Is everybody okay with why that can't happen here? There's no right angle. Okay. So we're going to have to go back to using the law of sines again. So when you are using the law of sines, when you have a non-right triangle, you will be using it several times. Okay. It's not like your trig ratios where like lots of times you can do one of those and then you can figure everything else out. So our last equation to solve would say sine, I'm just going to use the original pair, sine of 42 over 63. But now I'm going to try and solve for side length C. So I'm going to have to use the sine of 100.7 on this side. And then I'll go through cross multiplying and solving again. So 63 multiplies the sine of 100.7 and C multiplies the sine of 42. And to get C alone, we'll divide by the sine of 42. You'll notice lots of calculator work, so you want to be good at using your calculator. And that should give us 92.5. So C is equal to 92.5. If you're concerned about how big that number is, remember it is across from the largest angle in this triangle, and that largest angle is significantly bigger than the other angles in the triangle, right? 100 is a lot more than 37 or 42 degrees, okay? Right, any questions on using the law of sines? You sure? No? All right, take 1 minute at your table before we talk about the law of cosines. Okay, so the next law that we're going to use is law of cosines. Before we get there, though, I want to kind of show you why would we have to learn another law, right? We have all this right triangle stuff. They figured out this one thing. Why do we need another one? So I'm just going to show you a sketch of the first example, then we'll fill in the formulas and then figure out how to do it. There's no triangle drawn in the first example, and it doesn't say it's a right triangle. So when that happens, you just want to give yourself a generic triangle, not assuming that it's a right triangle because it doesn't say any of them are. And we know we're going to use the letters A, B, and C because of the letters they're using in the problem, okay? And we know we'll put the lowercase letters opposite of their corresponding angles. And then I'm going to fill in the information that they did give here. So angle A is 47 degrees, side C is 27, and side B is 22. Okay. So here's all the tools we have for solving triangles. Tool number 1, all triangles have 180 degrees. Does that help us right now in this triangle? No. Tool number 2, Pythagorean theorem. In right triangles, if you have two sides, you can find the third side. Does that apply to this triangle right here? No, we don't have enough information to know if it's a right triangle. Tool number 3, trig ratios, sine, cosine, tangent ratios. Can we for sure use those in this triangle? Do we know that right now? No, because it's not a right triangle, okay? Tool number 4, law of sines, okay? So you'd feel like this is your hope, right? We just set it up. If we try to set up the law of sines for this, and you guys don't have to write this down, but I just want you to see that there is actually a need for the other rule. It's not just randomly made up. If I try to set up the law of sines right now, the only angle I have is 47, so I'd go to use that. And what's across from my 47-degree angle? Side A, unknown. Then I want to go set up the other one, but if I'm going to solve for A, I need a number here and a number here, I have two side lengths, B or C. Let's say I decide to use B, right? It's 22. But then what goes in here for the angle? I don't know it. That's not going to work. See how that's not solvable? Okay, that's one equation with two different variables in it. I can cross multiply stuff, but I'm not going to be able to solve for anything. So law of sines is super powerful. Unfortunately, not powerful enough to solve every instance of the triangle. So we needed one more law, the law of cosines. We don't need the law of tangents because between the law of sines and law of cosines, there is enough to solve any triangle, okay? So law of cosines formulas are much more complicated, but you guys aren't memorizing them, so you shouldn't have to worry about that. They kind of look like Pythagorean theorem with stuff subtracted from them. So they basically say one of the sides of the triangle squared is equal to the other two sides squared and added together. That's why it kind of looks like Pythagorean theorem-ish. But then with some stuff subtracted from it, and the stuff that's subtracted is 2 times the side lengths that you just added together. So because B and C were being added together, those are the things I'm multiplying here. And then that is multiplied by the cosine of the angle across from the side that's on its own over here. So angle A. Super complicated, but again, you're not memorizing. You just have to use it. But it means it will be a little more work in solving than what we saw before, right? Because there's a lot of stuff. And then this relationship, just like the law of sines, this same relationship is true for any side that you pick. So you can put the B squared over here, and then the two sides on the other side of the equation become the A and the C. But the angle that you're using here would be angle B. Or you can put C on its own on this side. And then you're using A and B as the side lengths, but the angle you're using is angle C. Okay, so always the angle we're using in the formula here is across from the side that you're like kind of solving for, or is by itself over here, and the other two sides are what's being used in the arithmetic on the side that has like a lot of stuff going on. Okay, but again, you don't have to memorize. We just want to use it. So we definitely need to use it in the triangle we were just looking at because the law of sines didn't work, right? We tried literally every tool that we had and couldn't get anywhere in this triangle. So in this triangle, our last hope is that this law of cosines is going to work for us. So again, we're trying to find side A, side B, side C. And we have two of these. And then angle A, angle B, angle C. We have angle A. Okay. We tried everything, it didn't work. At least we know there was actually a need for this very complicated looking formula. And now we're going to try and use this very complicated looking formula. There are actually lots of ways that we could plug in and use, but what do you guys really want to find on this triangle? What if we found on this triangle we could have actually used law of sines if we had one more piece of information? What piece do we need? Side A, right? Okay, that would make our lives a lot easier. So I'm going to see if I can use law of cosines to find side A. So look at the cosines formula. If my emphasis is on finding side A, then I want to be able to plug in B's and C's. Do we have sides B and C? And I want to plug in angle A. Do we have angle A? Yes. So basically, even though it's complicated, I'm just going to have the thing I'm finding on one side and numbers to plug in for everything else on the other side. So A can be found, or A squared can be found by doing B squared plus C squared minus 2 times B times C times the cosine of angle A. Honestly, I'm giving you guys the formula, so it's not the formula that's the problem. You just really got to be careful with your calculator because there's a lot of stuff to input. If you have a calculator like the graphing or the scientific ones that let you type stuff in, you can literally just type in that whole entire thing as you see it, because the calculator knows order of operations and to multiply and stuff before. So I'm going to type in 22 squared plus 27 squared minus 2 times 22 times 27 times cosine of 47. I'm going to tell you guys what I get so you can see if you plugged it in right. I end up getting, I'm going to write a few decimals because I'm not done with my calculation yet, 402.7859. Now, that doesn't make much sense, but it shouldn't make sense because that's A squared. Okay, so kind of like Pythagorean theorem, what do I have to do here to finish off and actually find the side length? I need to take the square root of that. And when I take the square root of that value, I get 20.069, so I'm going to call it 20.1. Does that number make more sense with our triangle? Okay, seems to be in the realm of what those values are. And so I just figured out side A. Now, you can go solve more stuff using law of cosines if you want, but it's just like a lot of work because the formula is really long and has lots of pieces to it. Usually, once I find the one piece I need from law of cosines, then I would go and then use law of sines, okay? And so we're going to work on that. There is one thing I want you guys to write down, and unfortunately, it's probably not going to make a huge amount of sense for this, but if you're using law of sines to find an angle, which is what we're about to do, right? Because the only thing that's missing in this triangle are angles. Sometimes you don't have a choice, but if you have a choice, okay, you need to save the biggest for last. You know how they say, save the best for last. Save the biggest angle for last, okay? Here's why. Your calculator's been programmed a very specific way. Any of you have actually seen the unit circle and done inverse sine and cosine? There's nothing you can type into this to do inverse sine on your calculator that will ever give you an obtuse angle. Never. It might say undefined. Otherwise, it can give you negative angles. It can give you positive angles, but it will not go past negative 90 and 90. It will only give you answers between negative 90 and 90. There's a reason for this, okay? We'll maybe touch on it later, but that's the way it's programmed because of some like structures that we've set up in the world of trigonometry. But that means if I'm trying to find an angle that might be obtuse, that sucks because my calculator is not going to give me an obtuse answer, okay? So we just need to make sure if there's any angle that might be obtuse, find something else first, okay? So when we look at this triangle, if there was an obtuse angle in this triangle, which angle would it have to be? C. How do we know that for people that are like, how would you know? They all look the same. I drew this generic triangle, right? So C doesn't look any bigger than anything else. How do I know that C, if there is an obtuse angle, is the one in this triangle? Good, it has the biggest side across from it. So C is the biggest angle. That means I'm going to go find B first. That's all that means. Is that okay with everybody? Because my calculator, if I find C first, I don't know if it's obtuse or not, but if it is, my calculator will not give me the right answer. Does that make sense to everybody? Okay. And then you could do it that way and like do this huge analysis, but like that's not going to help you and you guys don't have enough background, I don't think, to do that. So we're going to find B in this case. So we're going to set up sine of 47 now that we have side A over 20.1. And we're going to look specifically for angle B, which is across from the side that's 22. So I usually only ever have to use law of cosines one time because then I have enough information to go back to using law of sines. Personally, I just like it better because it's a simpler formula and I have something that I can kind of repeat over and over again that I'm more used to solve it. Okay? So 22 will multiply the sine of 47. 20.1 will multiply the sine of B. And then we'll divide by 20.1 to try and get B alone. And I'm going to do it the way I did before just because you guys do have access to a calculator and you tend to be more comfortable, less expressions and more numbers. We can actually find the value of the left side of this equation, which turns out to be 0.8005. If I round to 4 digits. And then the last step in solving this is to take the inverse sine of each side. So angle B will be equal to the inverse sine of that decimal value. When you guys do that, you should get 53.2 degrees. And so now, how will we find angle C? We'll just add them up and subtract from 180, and that's why we save the like the one that could be obtuse for last. Because if it is, this will work and find it because we won't use sines again to do it. So I'm just going to add together 47 and 53.2, subtract those from 180, and I get 79.8, which means, did it really matter that I saved angle C for last? No, it would have been fine, but did I know that it would be fine? No, so it's better to just save what's possibly an obtuse angle for last. You'll only come across that in situations like these, because in our previous situations we saw with law of sines, there was only like one angle we could solve for or something like that, okay? Is everybody okay with what these laws look like? Okay, we're not going to do more examples, but we are going to do one more. What if you were using law of cosines to solve for the angle? Okay, so like what if they gave you all three sides? That's why I don't want to do the other examples on here. So let's say they gave you like three sides of a triangle. So here's my generic little triangle. So we have this information. Do you guys see why we can't use trig? We can't use that the angles add up to 180 because we don't even have one of them. Do you see why we can't use law of sines in this instance? We don't have any angles to like set up in the equations. So you would have to use law of cosines in this instance as well. But what would you be solving for in your law of cosine formula? Look at the formulas for law of cosines. In all the formulas, they have spots for all three sides in every version of it, right? Like here's side C, side A, side B, more of the sides, and then they have an angle. If I have all three sides, I have stuff to plug in everywhere except for the angle. And so I just want to show you one time, because people often solve for it incorrectly. They set it all up right, but they don't solve for it correctly, what it would look like to solve for an angle in that instance, okay? So in this instance, and with law of cosines, I know this seems weird. It doesn't matter which angle you solve for first. It doesn't have to be because cosine doesn't have the same restrictions. Every time you type inverse cosine of something on your calculator, it will never give you a negative answer, but it will give you some number between 0 and 180. That's what it will give you every single time, or it will be undefined because you entered in something that doesn't work. So it doesn't matter here, obtuse, not obtuse. So I don't care. What angle do you guys want to try and find? A, B, or C? A? Okay, they like first letter of the alphabet. Sure. I'm going to focus on finding angle A. All that means for me is I need to use the version of the equation where it ends with the cosine of A, because I'm trying to find A. We're not doing this. I just gave you guys an example of having all three sides. Is that okay? No, that's okay. So I want to use the formula that uses A since I'm trying to find angle A. And so if you guys look back at that law of cosines, that means the side across from A is over here by itself. And then B and C are what we plug in here. All right. Here's what people do incorrectly. I'm going to take a few steps here because I want you guys to see. So 5 squared is 25. 7 squared is 49. 10 squared is 100. 2 times 7 is 14 times 10 is 140. And you guys have calculators, so like even if you couldn't do the arithmetic in your head, it's there. Look here. Most people are good about getting here. And then here's what they do wrong. They know they want to move stuff to the other side to get A alone. And so they do like 49 plus 100 minus 140. Okay. Here's what I need you guys to recognize about that. That's not okay. This is like having, here, we'll even combine together the 100 and the 49, okay? That makes 149. That cannot be combined with the 140, okay? This is like having, you guys are perfectly good at it when it's X, but put that cosine in there and everybody's just like really not okay. This is like having this, right? This is the thing with the variable. Do we add together 149 and 140 over here in this equation? No. We move the 149 over and then divide by the 140. We need to think about this one in that same exact way. At this point, we can't combine together the 149 and 140. What we can do is we can subtract 149. And then we can divide by negative 140. And you guys have calculators, so you don't need to really do any work here. You can just keep it in a crazy fraction, because we're not done yet. I don't want to spend time reducing, right? You can turn it into a decimal, whatever you guys want. Now you're at a part that should look familiar, right? This should look familiar from solving our right triangles. We set up equations like this all the time. We just did one where we turned that into a decimal. How would I then solve for angle A? The inverse cosine. Are you guys okay with that idea that I'm trying to get the angle alone? So we would take the inverse of both sides. And on this side, that would just leave A. And just for those of you that are checking your calculator skills, when you do that, 124 over 140, you should get 27.66, which means angle A is equal to 27.7 degrees. Okay. I don't want to solve this whole triangle. I just wanted to show you guys, number one, there is an instance where you can't just like always plug it in the first way we did. You'll be using it this way. And number two, everyone does a great job setting up, but about 50% of the room every time doesn't finish solving it correctly. And a lot of the times you'll get an error because what you get doesn't make sense to the calculator that you're plugging in, because what you did to try and take the inverse cosine of something, you did kind of some illegal operations and steps to do that. So I just wanted to show you guys that so that we don't make those same mistakes. Is this okay with everybody? Yes. Okay,